Uh, this is the session 3, which is about computational concepts for organic, inorganic solar cells. I'm chairing the session on the behalf of Professor Francis Nyongesa, while my rapporteur is Dr. Nur Mulyuka. Let me just ask Kennedy Wamalwa whether he is ready to present, because Lynette says she is trying to recover. A computer is hanging, and if Kennedy is ready, can he start off, and then after he has done his presentation, then Lynette can come back. Is Kennedy Kaemba ready? Is Kennedy around? Kennedy? What about Wycliffe Soy? Wycliffe, are you ready? Wycliffe, are you around?
Yes, Prof.
Is it okay you start off to present, then
Hello?
Lynette can come later?
It's fine.
It's okay. Then let me welcome Wycliffe Isoy from University of Eldoret, and his presentation is on the thickness dependency of window layer on lead iodide ammonium perovskite solar cell. Well, welcome, Wycliffe. You have 15 minutes to make a presentation. Then question and the discussions will be done later after all the presenters have done. Yes, welcome.
Good afternoon, all. I want to welcome us to this presentation. As Prof mentioned, my name is Wycliffe Isoy, and I'm presenting a paper that we have written with my colleagues, Dr. Maxwell Mageto from MUST, Dr. Christopher Maganga from Kabarak, Professor Mambuli from University of Eldoret, Dr. Odali, and Dr. Selin from MUST. Thickness dependence of window layer on methylammonium lead iodide doped with chlorine peroxide solar cells. In introduction, I want to mention that as we all know, the demand for energy is on an increasing trend, and this is because of the technological advancements globally, and also the increase of populations. And the current major sources of energy, the holy servos, coal, and even gas, will be it's projected that it will be completely exploited in the near future. And this informs us that there is a need to find a clean, renewable, and sustainable source of energy. Solar energy has for a long time now been considered among the best alternative source of energy, owing to its abundance, but harvesting and conversion technology has been the limiting factor. And we do know that for decades now, silicon has remained the dominant material for the production of commercial solar cells. But again, we do know that silicon solar cells is faced with a lot of drawbacks. And that's why research is concentrated in finding the alternatives solar devices. And research seems to suggest that peroxides stand to be good candidates among other materials. Currently, peroxide is promising solar cells, and it has hit a convection efficiency of slightly above 24%. But in order for us to even improve this efficiency of these solar cells, then we need to understand its operational mechanisms. And I want to note that simulation will give us, or will help us understand the operational mechanism of the solar cells and therefore improve its efficiency. Simulations again will help us even project the higher conversion efficiency of these cells with the designed, with the controlled design. In a numerical model for the peroxide solar cells and the material parameters, as I mentioned that the understanding of these operational mechanism simulation will help us. Naturally, our work, we use simulation to help us project or rather improve the efficiency of peroxide solar cells. In the designing and characterizing of methyl ammonium lead iodide doped with the chlorine, we used the simulation tool SCAPS 1D, and the solar cell structure as shown in our figure 1. It consists of fluorine doped tin oxide, TiO2 material thin films on a glass substrate. It also consisted of methyl ammonium lead iodide doped with chlorine as an absorber layer. It also consists of aspirometrid as a whole transport layer and silver back contact as shown in this figure here. And again from SCAP, we were able to get the NH band structure as shown here. And from this band structure, it's evident that for an absorber layer with a very small band gap, but with our FTO TiO2, with a larger band gap, it can absorb most of the radiations. And the one thing I also want to mention, in our simulation, the output solar cell performance for this case, the peroxide solar cell, was majorly based on the electrical, optical, and device parameters that were used in simulation. In our simulation, we were mostly concerned about the layer thicknesses, the layer thickness of FTO from our structure. We also simulated the layer thickness of TiO2 and the methyl ammonium lead iodide. All this was to help us get the optimum layer thicknesses that can help us improve the efficiency of the solar cell. Now, in our first results that we got, the ones that I've projected here, we were trying to see or investigated the output performance of the cell when we were changing the FTO thicknesses while holding all other layer parameters constant. We were varying our layer thickness FTO from 100 nanometers to 450 nanometers. And the one thing that the results that we got, we realized that the open circuit voltage remained constant, while the current density, the open current density, decreased as we increased the FTO thickness. And another result that we got is that as we increase the FTO thickness from 100 to about 450, the fill factor, here, it has a very small significant from about 7.77 to about almost 7.8, very small significant, but the efficiency reduced from about 70.84 all along to about, I beg your pardon, from about 23 to 0.1 to about 23. So you realize that as we increase the FTO thickness, then the efficiency dropped. There was a very small increase of fill factor. There was also a decrease in current density, and the open voltage remained constant. And again, when we changed the TiO2 thickness while holding other layer parameters constant, this is what we got. The open circuit voltage remained constant as we varied from 5 nanometer to about 100 nanometers. There was also a very small significant change in the current density. The same was also observed for the fill factor and the efficiency. And this informed us that the TiO2 thickness, the change that does not have much impact in the performance of the cell. But though, even if it does not have a major impact on the cell performance, but we realize that the TiO2 thickness between 5 and 100, it gave us a significant result of an improved one. Again, when we changed now, or when we were varying the thickness of the observer layer, while holding other layer parameters constant, this is what we got. The open circuit voltage reduced as we increased our observer layer thickness. Also, the current density increased up to from about 100 nanometer to 300 nanometers, then it became constant. Then for the fill factor, it reduced, though not very significant. Also for the efficiency of the cell also increased. So if our major aim was to find the optimum of film thicknesses, and from our study, then we did conclude that for FTO, 100 nanometer could give us the better performance of the cell, as evidenced from these results. And we also discovered that TiO2 thicknesses, the change in the variation of the TiO2 thickness does not alter with the cell performance, but we realized that even though it does not alter so much, but a film thickness TiO2 from 5 nanometer to about 100, it gave us significant results. Then the observer layer, as we change, Sorry? We realized that an increase beyond 400, about 400 observer thickness, it gave us it impacted negatively, or it reduced the cell performance of the cell. So we took 300 nanometer for the observer layer as our optimum. TiO2 we took 50, and for FTO we took 100 as our optimum layer thicknesses. And with this, we tried to investigate the JV characteristic of our cell. And the red one is from our simulated, and the literature of this black one, the dotted one, is what we got from the literature, the layer parameters we got from the literature. And we realized that with 100 FTO and a nanometer, with TiO2 50, and our observer layer 300, it gave us a significant improvement of the efficiency of the cell from 22.7 to about 29.56, which was a very significant improvement of the solar cell. In conclusion, I want to mention that the simulation revealed that the variation of TiO2 thickness has no significance change in the device performance, and an observer thickness from about 300 to 400 is suitable for the data performance of the cell. And hence, we did realize that the thick observer layer may have no much advantages as to the cell. And again, the simulation results further revealed that 100 nanometer, 50 nanometer, and 300 nanometer layer thicknesses for FTO, TiO2, and methylammonium iodide respectively gave a better performance of our cell as compared to 200, 50, and 600 nanometer thickness, of which we were comparing ourselves, which has been reported. I want to appreciate Msseesa for this platform. We have shared it with Msseesa University, and also Dr. Mark Blagan and his staff for the freely distributed SCARP simulator software. And after that, I say thank you.
Thank you for keeping it time. You actually took exactly 15 minutes. May I request the next presenter, Kennedy Wamalwa Kaemba. Kennedy.
Yes, present.
Yes, I think you are the next presenter.
Yes.
Yes. Kennedy will be presenting on the well chirality in a topological sentimental tantalum phosphide. Welcome, and keep time, 15 minutes, or if you can take less, because we have already lost some 3 minutes somewhere. Welcome.
Okay. Okay, thank you. I'm trying to share, but there is another screen being shared.
Wycliffe Isoe.
Yes.
Can you please you stop the sharing on your side so that the screen is available? Wycliffe?
Yes.
Yes. You can stop the presentation, the sharing.
Yeah, I've done it.
It is still visible on our screens. Okay, good. Yeah, Kayemba?
Okay, thank you. Okay, thank you for today's presentation. My name is Kenneth Wamalo Haemba, a master's student from Masinde Muliro University of Science and Technology. So this work that I'm going to present is the ongoing thesis work that I'm doing. I'm still working on it. My supervisors are Dr. Henry Barasa from Masinde Muliro University, Dr. George S. Manyali from Kaimosi Friends University College, and Dr. Isaac Amotoch from Masai Mara University. I'm trying to move to the next slide.
Kayemba, we cannot see the screen. We're just seeing a blank white screen. What is going on?
It is not visible.
No.
Is it visible now?
No, not yet.
Let's put it down. Let him put it down.
It's just stop
Can you
it.
try to use the arrow keys of the computer?
Stop sharing. Stop sharing.
I stop sharing, huh?
And then you share again.
Okay.
You open the PowerPoint first, then you share.
Okay.
Okay, Kennedy, let's help. We are helping you to present from this side. Eh?
Okay,
Okay.
now it's okay. I will share.
Okay, let's help you present from this side. Okay, Kennedy, so you can present, Kennedy.
Kindly enlarge the screen.
Professor Mambora, can you click? Okay, fine. Okay, Kennedy, try to recover some minutes because you have it's already 3 minutes past when you are supposed to have started.
Okay, thank you. Okay, thank you for today's presentation. I'm Kenneth Wamalo Haemba from Masinde Muliro University. This is my master's project which I'm doing. It's part of the thesis that I'm doing. And the topic of presentation is band inversion, well chirality, and topological transitions in tantalum phosphide. And my supervisors are Dr. Henry Barasa from Masinde Muliro University, Dr. George S. Manyali from Kaimosi Friends University College, and Dr. Isaac Amtoj from Masai Mara University. So this is the outline of what I'm going to discuss in this work: topological same metals, tantalum phosphide, objectives, methodology, research and discussion, conclusion, acknowledgement, and also cite some few references. Now, the first thing we're beginning with the topological same metals. In this class of material, we are going to discuss, I'm going to discuss the bulk properties of the materials. And in topological same metals, this is a same metal where the valency and conduction bands touch near the Fermi level. And at a point where they touch is called the Weyl node. So what to note, this material has three types of, we have three types of same metals. We have the Dirac same metal, we have the node line same metal, and we have the Weyl same metal. And tantalum phosphide belongs in a group of I41, that is a group 109, the primitive cell in the first brilliant zone. So TAP exists in three phases. We have the hexagonal phase, we have the rhombic phase, and we have the tetragonal phase. And in this material, I'm mainly going to discuss the tetragonal phase because this is the phase that has portrayed the topological properties. Now, other the experimental result has shown that TAP did not show phase transition up to about 27 gigapascals. It was done by Gupta and his team. And also the crystal structure for tantalum phosphide lacks partial inversion symmetry. However, they did not explain to what extent TAP remains a Weyl same metal. And therefore in this work, the band structure in TAP was calculated with the spin orbit coupling to show how the spin orbit interaction alters the single Weyl fermions. Now I have three main objectives in this work. The first one is to calculate the band inversion in tantalum phosphide so as to show the topology in TAP. Then two is to calculate the topological transition in TAP by employing modest pressures so as to avoid the phase transition from occurring. And the last objective in this work is to calculate the Weyl chirality in TAP in integration using the maximally localized Wanner functions. But in this work, I'm going to discuss the first two objectives because the work is still ongoing. Now, the methodology I adopted here, I use the state of art ab initio based on the density functional theory methods implemented in a Chester code. The exchange correlation were treated with the generalized gradient approximations, and the co-electrons were replaced by the ab initio non-conserving and the full separable Tolmadin pseudo potentials. And the Fermi-Dirac distribution with a temperature of 0.09 electron volts was used to smear the occupancy of one particle eigenstates. Still in methodology, in order to get the converged system, I used two way procedure. The first thing I began by the atomic structure, both with spin and without spin orbit coupling, and the one particle density matrix with the K point of 10 by 10 mesh was first relaxed. And secondly, freezing the relaxed structure and the density matrix. Now the non-self-consistent band structure calculation with the much denser sampling of about 60 by 60 was performed in relaxing the system. There are some high symmetrical points which are used in calculating the band structure in this case. And in real space integration, a uniform grid with an equivalent plane cutoff of about 600 Reinbach was used. And also relaxed the system until the forces were much smaller than 0.01 electron volt Bangstrom. So these are the results that I obtained. As I said, the first objective, I calculate the band structure both when we have the spin-orbit coupling and when without spin-orbit coupling, so that you can see the effect of applying the spin-orbit coupling to this particular system. Now, in this graph, there are two figures here. There is figure 1. In this band structure, I computed without the spin-orbit coupling so that I can be able to observe the band structure of this particular system. And as I mentioned earlier on, this tantalum phosphide has a whale fermion. A whale fermion is where the two bands they meet, they touch at near the Fermi level. So I can see at this particular point the bands are touching, and this line, the dotted line, is the Fermi energy for this particular structure. Now, still, if we look at along this particular line, we have the bands which are crossing. There are two crossings here. There is the first one here. There is another one here. So this one is without the spin orbit coupling. We have one whale fermion and we have two nodal crossings. Now I applied now the spin orbit coupling so that I can see how this particular system behaves. And as you can see in the second figure here, after applying the spin orbit coupling, there is something that is happening in this structure. One, you can see that there is an energy gap at this particular point. And this is as a result of applying the spin-orbit coupling to the system. Then another thing you can observe in this band structure, this region, there is a band inversion that is occurring at this particular region. And it's the effect of the spin-orbit coupling. And another one is that these bands, they are splitting. So that means when we apply the spin-orbit coupling, it also has an effect of splitting the bands, what we call the double degeneracy. And move to the next. Apart from the band structure, I also computed some other structural properties. I began by also calculating the volume of this system. Now, the main essence of calculating the volume is to get the minimum energy so that where the system has relaxed, so that as we look for other properties, we do it in a relaxed system. So when I was calculating the volume for this particular system, I was able to see that the minimum energy here for this system is about 121, electron volt per angstrom. And now that it is the 8 atoms that are used in the input file when I was computing, it means the volume per atom in this case was about 15.23 electron volt per angstrom. Can you move to the next? So I also computed other structural properties like the lattice parameters, bulk modulus, and also volume per atom. And in this particular table here, as you can see, I was able to get the lattice parameters. Like for A, I got 3.31. And if I compare with other studies like Cheng et al. Got 3.34, Lee et al. Got 3.32, and Besar et al. Got 3.32. The value for C, I was able to get 11.15. And you can see other studies what they got: 11.43 for Chang et al., 11.36 for Lee et al., and 11.34 for Besar et al. I also computed the bulk modulus, and I was able to get 130.42. By the time I was computing this, I didn't get the results for bulk modulus for other studies. And the volume per atom is 15.23, which is also very close to other studies. So as we move to the next, we can see that the results I obtain here is much in agreement with other studies. In objective 2, I talked about applying some modest pressure to the system so that I can see how it behaves. And here, as I was applying the pressure, I began by applying the pressure of about a tune of 0.1 to 0.5 gigapascals. And when I was doing so, actually there was no transition at that particular point. However, when I increased the pressure up to about 9.974 at this particular point, you can see that there are three graphs in this particular graph. We have the red for monoclinic, the black for tetragonal, and the green for orthorhombic. So when applied pressure of this particular region, about 9.97 gigapascals, you can see that here.
You have 1 minute remaining.
Okay. You can see that here it was able to transit from the orthorhombic to monoclinic. Then for about a pressure of 13.34, it was able to change to the tetragonal phase next. So I think this is what I've just explained in the graph. We can move to the next. So I was able to calculate also the volume for the three graphs so that I get which phase has the minimum energy, minimum volume. And as you can see from this graph, it's the tetragonal phase that has the minimum volume. We can move to the next. So as I conclude, I was able to observe the energy gap when I applied the spin-orbit coupling. Then I've also able to note that actually the tetragonal phase is the most stable phase. And in this particular phase, there is no topological transition. And the other parameters were very much in agreement with the other studies. Next. So as I finish, I wanted to acknowledge first the Msseesa for giving me this platform for presenting this research, and also the Center for High Supercomputing, where I've been running my calculations. The most have my supervisors, Kaimosi, Masai Mara, and also in collaboration with the technical Catholic University and also the CTEP team. I also cited some few references. The next page, the next slide, there were a few references that I was able to cite. I want to say thank you for giving me this opportunity. Bless you.
Thank you, Kennedy, for your presentation. You have actually taken 16 minutes. Thank you. Let me call upon the next presenter. That is Lynette Allen. Lynette, please load your presentation.
We are going to project for Lynette.
Okay, do it. And as the presentation for Lynette is being loaded, let Clinton Oyomo be on standby immediately after Lynette makes the presentation, so that he can take over immediately, so that afterward it is a fielding of questions. Professor Mabora, are you already with the presentation for Lynette Allen? Is Mabora around? I can see his mic is muted.
It's been loaded, eh? It's been loaded. Be patient.
Okay. Or do we go to the next candidate while you are preparing to be ready? Professor Mabora?
Yeah, call the next candidate. The presentation is
Okay.
not downloading.
I think I've been able to.
Ah, okay. She's there now.
Are you presenting using a mobile phone?
Yes. My laptop is hanging.
I don't know
Is
whether
it
this
okay?
one will let you give us a full screen.
Okay, then maybe you can
Or
load the
you-
next presenter.
Or we go to the next presenter, then you send that to me. I project it for you while the other presenter is doing it.
It's okay.
Bill Oyomo, are you ready? Bill Oyomo.
Yes. Yes.
Yes. Lynette, you can remove yours. Let Bill do it, and then you send yours to me. I project for you. Okay. Welcome, Bill.
Okay. Thanks. Okay. I hope everyone can see.
Not yet. It's coming. Okay,
Great.
you make it a full screen. Is it possible to make it a full screen? So as he tries to make it a full screen, the presentation by Bill Oyomo, it's the title is the thermoelectric transport properties of tin selenide from first principle calculations.
Okay. Let's make it full screen.
Okay, I think you can proceed as it is. We can still see it.
Okay. Okay. My name is Bill Clinton Oyomo from the Technical University of Kenya. I'm an undergraduate student of Technical and Applied Physics. Today I'm presenting the thermoelectric transport properties of tin selenide from first principle calculations. So, the introduction and define some terms. So thermoelectricity, which is otherwise also known as thermoelectric effect, refers to a group of phenomena that involves the interconversion between heat and electricity. That is the Seebeck and the Belcher effects, where Seebeck effect is the conversion of the temperature difference into electric potential. The Belcher effect is the conversion of an electric potential to heat, which can either be absorbed or evolved at the junctions of two similar materials. So the efficiency of thermoelectric materials to do the conversion is determined by the so-called figure of merit, ZT, which is equal to the Seebeck coefficient square times the electrical conductivity times the temperature all over the total thermal conductivity, Ke plus L, where Ke is the thermal conductivity due to electrons and Kl thermal conductivity due to lattice vibration. So, and then from the formula of Zt, then you can see that thermoelectric material for high efficiency, the Seebeck coefficient needs to be high, as well as the electrical conductivity, and consequently the lattice thermal conductivity and the electron thermal conductivity need to be as low as possible. So in the next slide, just trying to explain how the thermoelectric modules, how they work. So in the first setup, figure 1, that's a setup for a thermoelectric generator. It's composed of two materials. One is N-type, the other one is P-type. So when you have some source of heat, then the heat is concentrated on one side. It makes the electrons to diffuse to the cold side, and hence current flows in the opposite direction of the electrons and in the direction of the holes, creating that potential difference, hence generating current. It's applied in radioisotope thermoelectric generators in deep space telescopes away from the sun, where photovoltaic cells cannot be used. So the second module is the thermoelectric cooler, which works the principle that's opposite to the thermoelectric generator. In this case, it is when electric current is applied to such a setup, then heat is generated. The heat is evolved at one point. That heat, which is evolved at one point, it's absorbed. Hello, can you hear me?
Yeah, we can hear you loud and
Hello.
clear. Yes, clear.
Okay, I was seeing. Okay, so a thermoelectric cooler, in the thermoelectric cooler setup, when electric current is applied, heat is absorbed at one point, and that heat is transferred by the electrons and the holes to the other side of the setup, and then it is dissipated. It's applied in the cooling of IR detectors, lasers, frequency stabilization, automotive seat temperature control. So why tin selenide? As others have mentioned before, lead is toxic, as has been mentioned by other presenters. So we find that lead chalcogenides, for example, lead telluride, are best thermoelectric materials that meet to high temperatures, while bismuth chalcogenides like bismuth selenide and bismuth telluride perform best at room temperature. So, however, due to lead being toxic, it's a major environmental concern, and also bismuth and tellurium are expensive, so these limit large-scale applications of these devices. So tin selenide comes into play here because it's composed of earth-abundant elements, tin and selenium, which are also environmentally benign. Hence, this could be an ideal alternative for low-cost, environmentally friendly thermoelectric applications. So the objectives of my study was to, first one, to calculate the band structure and the projected density of states of the material, to determine the electrical conductivity of tin selenide, SNAC, calculate the electron thermal conductivity and the Seebeck coefficient of the bulk material. The methodology that was employed here used the quantum espresso code as implemented. Quantum espresso code was used within the framework of the density functional theory for electronic structure calculations, and then a generalized gradient approximation parameterized in the form of PBE exchange and correlation function was used. The ultrasonic pseudopotential approach for treating the valence electrons, and then the kinetic energy cutoff was set to 80 Rydberg. The Brillouin zones sampled by a 2 by 10 by 10 mesh grid. The thermoelectric properties were then calculated using the Bootstrap code that solves the Boltzmann transport equation under the constant relaxation time approximation. So a little bit of theory about DFT. It's a ground state approach for determining the properties of materials. So it works by converting the many-body equation to non-interacting single particle equations known as the Kohn-Sham equations, which are given there. So when these equations are solved, then the ground state properties can be computed. So a little bit about the Boltzmann transport equation, because the code I was using, the Bootstrap code, it solves the Boltzmann transport equation, which is given by that equation as given there. where tau, given by that symbol, is the relaxation time. The general solution is given there, where F is the distribution function out of equilibrium, and F naught is the distribution function in equilibrium. So if this equation is solved, the various transport properties can be obtained. That's what the code does. So let me go to the results. So this is the structure of tin selenide, the relaxed and optimized structure. It's an orthorhombic crystal structure at room temperature with 8 atoms per unit cell. The experimental lattice parameters, bond lengths, and bond angles obtained in this work against the experimental lattice parameters, bond angles, and bond lengths against the theoretical values obtained are shown in table 1, and the deviation. There seems to be some small positive deviation. This is expected due to the generalized gradient approximation that was used, which tends to overestimate the lattice constant. And then on this slide, figure 4, this one shows just the same structure, but from different crystallographic planes, the YX, ZX, and YZ planes, and how the electrons are distributed along those planes. So the band structure was obtained, is shown in figure 5. The material was found to have an indirect band gap of that value 0.625 between the high symmetry points gamma X and gamma, and Y gamma. It's also shown in the diagram, the conduction band minimum and valence band maximum. From those 2 points, that's where the indirect gap was measured. So when we look at the pido structure of the material, then it's evident that the selenium 4p orbitals and tin 5p orbitals are dominant on the conduction band, while on the valence band, the 5p tin orbitals and selenium 4p orbitals contribute mainly to the valence band. Selenium 4p states and 5p tin orbitals, while the 5s tin and SE 4s states offer very little contribution to the conduction to the valence band. So, and then this is the variation of the electrical conductivity versus temperature. The graph in figure 6, the y-axis, the conductivity given in sigma per tau, that is sigma in terms of the relaxation time, and the temperature increased from 50 all the way to 800 Kelvin. So the electrical conductivity was found to be directly proportional to temperature, which suggests a semiconducting property. And the increase was more pronounced on the A and the C axis, while the B axis exhibits very low electrical conductivity than the other 2 axes. And this anisotropy is attributed to the high electron mobility on the AC plane of the SNAC compared to the BC plane. It's also worth noting that these calculations were performed at a temperature of 11 below the melting point of SNAC, that is 1134. The next one is the electron thermal conductivity versus temperature, how the electron conductivity behaves as the temperature increases. It's the same as the electrical conductivity, but the values of the electron thermal conductivity are quite low as compared to the electrical conductivity. The electron thermal conductivity was also found to be anisotropy in that the B and C axis demonstrated a high electron thermal conductivity than the A axis. So this anisotropy may be attributed to the fact that the AC plane, the BC plane has a higher electron density than the AC plane. I was also able to get the Seebeck coefficient as a function of temperature for the same material. So for Seebeck coefficient,
1 minute.
Okay. For Seebeck coefficient, the B-axis was found to be having a higher Seebeck coefficient as compared to the other two axes shown in the graph. The red one, that's the B-axis, while the C-axis showed, and the Seebeck coefficient was observed in that range, 251 microvolts per Kelvin at 300 Kelvin, and increased to, and as the temperature increased to 800 K, the Seebeck coefficient was found to be 249 microvolts per Kelvin. So as I conclude, I can say that the calculation of these properties using first principle methods proved to be insightful. I was able to get the band structure, but it was slightly lower than the experimental value. This is understood as EFT tends to underestimate the band structure. Also, the electrical conductivity of the material was also found to be increasing significantly with the temperature. I've given the range there, which is very good. Shows that the material is a very good conductor at high temperatures. On the other hand, the electron thermal conductivity was also found to increase with the temperature, but was low on the A-axis. The Seebeck coefficient was found to be in the range of 234 microvolts to 251. It is also a very good value. It is sufficiently high enough, if not excellent, and is enough for electric applications. So here are the selected references that I've cited. And I would also like to thank the Center for High Performance Computing, CHPC, for the computational resources that was used in doing the electron structure calculations, the materials modeling group of the Technical University of Kenya for the support and constant discussions that I have been with them, then my supervisors and advisors, academic. Thank you.
Thank you, Bill Oyemo, for that presentation. I think now you can remove the presentation so that the next presenter can upload the presentation. Okay, now the next presentation is going to be done by Lynette Allen. The title of the presentation is Ab Initio Studies of Structural and Electronic Properties of Selected Titanium Oxide and Oxynitride. Welcome, Lynette.
Thank you. I'm Lynette Allen, as you've been told, an MSc student at University of Nairobi, presenting on ab initio studies of structural and electronic properties of selected titanium oxides and oxynitrides. We selected some titanium oxides and some oxynitrides to study their properties, because we know first principle study of property of material is very essential when we want to decide on the best area of application. So I may not mention most of the things that my co-presenters who presented on the DFT that we are talking about have mentioned just because of time. Yeah, in our introduction, we are studying these materials because of their applications in water treatment and photovoltaics. These are essential needs in our society that need to be addressed. And titanium dioxide is an abundant material. It is chemically stable and highly versatile. It has various applications. So it has been doped by other elements so as to alter its band gap to enable it to be used more in photoactivity. But the higher oxide phases of titanium have not been adequately explored. And given this, our objectives are to study the structural and electronic properties of titanium dioxide. Kindly next slide. And specifically, we are going to study the pristine structures, and then we are going to
Hello, it looks
Linet,
like
are you there?
Linet disappeared. Let's look for her. Nicola.
into a problem that can be solved. I'm on the next slide. Into a problem that can be solved. It simply offers itself as a method of choice since it works with electron density that is easily understood rather than the many body Schrodinger equation.
We can't hear her.
Linet, are you still there? We can't hear you. Linet, can you, is it your mic muted or?
No, it's not.
Yeah, we can't hear you.
Okay, are you now able to hear me?
Now loud and clear.
Now we can hear you.
Fine. I am already at the 6th slide, but I can see my slides are not moving. Yeah, I was talking about the methodology and stating that we treated the exchange and correlation within GGA, generalized gradient approximation, with two flavors, the PB and PB sol, just to check on how these affect the lattice parameters. And we relaxed all the structures. The core electrons were replaced by ultrasoft, which offer faster convergence. And after going through the standard convergence procedure, a cutoff energy of 60 ROI was realized, and the Brownian zone integration was performed at the converged K points for those specific materials. Next slide. These are our results. These are our optimized structures. We studied anatase, rutile tier 2, and coronium Ti2O3, which is a high oxide phase of titanium. So we can see the first two, anatase and rutile, are tetragonal structures, while the other one is a trigonal structure. So after viewing our structures, we studied the lattice parameters within the two functionals And we found out that these the A were a bit higher than the experimental value, which is expected when you're working on GGA. And PB-SOL was giving values that are closer to experimental. So this comparative study suggested that the ground state properties of materials are highly dependent on the choice of exchange and correlation functional. And PB-SOL proved to describe the materials better than PB, so it was used for the rest of the calculations in this study. We then moved on to do a doping. We used nitrogen as a dopant. The doping was done in a supercell, 2x2x2 supercell for rutile and 2x2x1 supercell for anatase. And we substituted nitrogen at oxygen sites, as you can see. So our first diagram represents the two structures, the anatase and rutile, TiO2 doped at 2%. Then the next ones are representing, next slide, representing the two doped at 4%. The percentage dopant concentration were calculated in terms of the total number of atoms in the system. That is how we achieved the 2% and the 4%. We tried 6%, we shall discuss what happened there. Then when we now checked on the impact of the dopant on the lattice parameters, we found out that there were some deviations on the bond length. The bond lengths were reduced, as you can see, and this is attributed to the fact that nitrogen has a smaller atomic radius compared to that of oxygen. But generally, the structures appear to be preserved. So we can say that nitrogen is a good dopant structurally. Then we now went ahead and studied the electronic properties. For the pristine materials, pristine anatase, we have the band structure. We were studying the electronic properties by focusing on the impact of the dopant on the band gap, because we have stated earlier that we need to reduce the band gap of TiO2 so that it can absorb major part of the spectrum. So we got an indirect band gap of 2.29 between Z and gamma, we can see that. And from PIDOs, we can see that the band gap character is oxygen 2p and titanium 3d. So there's some strong hybridization between the two. When we doped this at 2%, we found out that the band gaps reduced. For at 2%, reduced to 1.81 and further reduced at 4%. And this reduction was attributed to nitrogen, because if you look at the PIDOs, you can see that nitrogen 2p states are the ones contributing to the reduction of the band gap. However, at 4%, we can see some impurity states within the intrinsic band gap of the materials. So at those points, these impurity states, they have been observed to act as recombination centers. So they make the materials not very good for applications in catalysis and photovoltaics. We observed that. And when we checked on the rutile, the pristine rutile structure, a direct band gap of 2.109. These band gaps are underestimated as expected in DFT because we are working at ground state. So we got that. The band gap character was titanium 3D for the pristine material, oxygen 2p, titanium 3D being dominant on the conduction band, and oxygen dominates titanium 3D is dominant on the valence band, while the oxygen is dominant. Oxygen, valence, titanium, conduction. Yeah, that's what you can see. And you can also see the energy ranges. The same thing that you observed in anatase is still observed here, that the band gaps are reducing for the doped materials. Next slide, the band gaps are reducing. And what contributes majorly to the reduction of these band gaps is nitrogen 2p orbitals. This was also observed by some researchers And they attributed this to the reduction of titanium when we replaced nitrogen at oxygen sites in their TiO2 doped nitrogen. That was Khan et al. In 2012. So generally, we have seen that the band gaps are reducing as the dopant concentration is increased. However, mid gaps are also forming, which is not a very good observation for the purposes of application of these materials, especially in photovoltaics and photocatalysis. So this, therefore, led us to take a look at corundum Ti2O3 as well as its oxynitride and see whether we'll have better results than that. So we did the electronic properties for the band gap calculations for the corundum Ti2O3, which is a parent base of the titanium oxynitride, that formula, which appeared metallic. Actually, we can see the position of the Fermi level, the red line. It's appearing to be metallic. This was not a unique finding from us. It is consistent with other DFT findings. However, this material has been reported experimentally to be a semiconductor. So we had to employ GFT plus U, which is known to correct band gap of materials, to try and get a more relevant band gap of this material. It is GFT plus U is one of the corrective approaches that is employed to
Looks
relieve
like Lynette is lost again. She's okay.
Am I okay? As in, can you hear me?
You are okay. I don't know whether it's Professor Mobora's side where he is losing you.
Okay, fine. So I was saying that since this material appeared metallic, yet it's expected to be a semiconductor, we employed DFT plus U, which is a corrective approach that is used to relieve DFT of electronic band gap approximation. It is reliable. It has been used before. It has a critical advantage of considerable low computational cost. So of course we have to optimize the U before we use it. So we optimize our U by just tuning different values of U while seeking an agreement with the experimental data of the system's properties. And it's corrected, DFT plus U actually corrects localization of D and F electrons in highly correlated systems. And we have titanium 3D. That is where it was applied. We corrected our band gap to 1.638 when U was equivalent to 5 EV. Then we went ahead and substituted the Ti2O3. We substituted nitrogen so that we are able to get Ti2N2O, the oxynitride. And we substituted this in the ratio of the elements on the formula. We had an option of having 15 possibilities. That you can find 15 when you work out the permutation, the number of ways in which 4 nitrogens can be substituted into 6 oxygens. So that is 6 factorial, 4 factorial, 2 factorial, which gives us 15. But we didn't consider all these 15 possibilities because of the nature of the parent structure. So we simply consider the 3 because the way the parent structure is structured. So we can see we have P1, P2, and P3, where we are having, we have substituted nitrogen in the ratio 2:1 to titanium, nitrogen, and 1 oxygen. And we checked the stability of this. We checked on their energy, and we were looking at the most stable, the one that we are likely to find. So the most stable, the one that appeared most stable was P1. And there was also an option of modeling these oxynitrides using a conventional hexagonal cells of Ti2O3, which had 12 titanium atoms and 8 oxygen atoms. We tried these as well, viewed using X-crystal at different angles of projection. And the projection in the direction of A plus B was giving us a better view of a good number of atoms. So that is what we use to view our samples when we are trying to dope the structures in the same ratio to maintain the ratio in our oxynitride. So again, with the samples, we checked on their stability to find out which was the most stable, the one that you're likely to get. We found that S1 was the most stable sample. So now we have S and P samples. Yeah, I've talked about that, where we were substituting, and we have the 7 samples. So now we have the S and the P samples, and we want to check and see which ones are more stable. So we check the energy per formula units of the lattice parameters and got that the most stable ones were the P structures. And remember that in the P structures, P1 was the most stable. So we decided to study the band structure of the P1, which is the most stable sample. So in the band structure of the P1, we can actually see that we are having strong hybridization between nitrogen 2p and titanium 3d orbitals within the range of -4 to 0 eV in the valence band. And
you are already 1 minute past the time.
And 4 eV in the conduction band. So there were no mid-gap states. That was something good to notice when we checked on these oxynitrides. So these oxynitrides appear to be more promising photocatalytic or photovoltaic materials compared to pristine TiO2 doped nitrogen, and the corundum Ti2O3. The band gap of the most stable one was 2.2 eV, that is P1. Just going back slightly, the band gap is a direct gap of 2.2 eV. This is clearly near the middle of the visible light. So we have a major part of the spectrum being used. And there were no in-gap states, so meaning absorption threshold will not be affected when we use this kind of oxynitride. These are some of the references used. We'd like to acknowledge ISP for funding. I want to acknowledge Materials Modeling Group at TK for the constructive discussions that we had, and CHPC for computing resources, University of Nairobi for providing the platform to undertake this research, and Msseesa for the platform to present my work. Thank you for your attention.
Thank you for the presentation. Now it's question time, and members of audience can now field the questions to Wycliffe Isoe, Kennedy Wamalwa, Lynette Allen, and Bill Oyomo. Questions are now welcome. Questions from the audience. Question from the audience.
I have a question for Bill Oyomo.
Yes, Charles Mogunde.
About electrical conductivity.
Yes.
And how SNSE,
yes,
the ratios, how they were affecting conductivity.
Sorry, how what?
SNSE,
yes.
Their ratios, these elements, how they were affecting each other on conductivity.
The ratios of the elements.
Yes,
I don't quite understand.
On objective 1.
Objective 1.
Yes.
Objective 1 was calculating the band structure. Oh, you are saying the determination of electrical conductivity of SNAC.
Yes, that's the point I wanted you to be clear. Objective 1, electrical conductivity. Or did you determine the ratios of these elements, how they were affecting the conductivity?
Okay, actually, I did not determine the okay, it was a the theoretical work.
Okay.
It was a simulation.
Okay.
So the ratio of the materials I could not determine.
So I believe it is a semiconductor. That's why I was concerned. Thank you.
Yeah, it's a semiconductor materials, and it's a P-type material actually.
Okay. Thank you. Thank you.
Okay, thank you, Charles. Fielding questions to the presenters. We have a question from the floor. Question from the floor.
Hello, Prof.
Yes, Nuru Mujuka.
A question to Oyomo, a general one.
Yes, please.
How do you see the future of thermoelectric devices? Are we expecting to see, wide application or wide use of these devices, in the near future for local people?
Sorry, come up again.
I asked the general question, how do you see the future of thermoelectric devices? Are we going to see wide use of these devices to local people in the near future?
Oh, okay, yes. Provided the problem is they are expensive, these thermoelectric materials, and also so provided we can get thermoelectric materials that are of low cost, then we can see there are wide applications even for locals. Like for example, currently there's a car company in the US called the Chevy Suburban, which is working on developing thermoelectric generators to embed them in the exhaust of vehicles so that they can convert the excess heat that is lost through the exhaust to convert it to electricity and to be utilized in the cars for lighting and the air conditioning of the vehicles. So it's possible, it can be.
Okay,
Thank you for that answer. Is it a satisfactory, Nuru?
Yeah, I think, yes.
Okay, good. Kennedy Wamalo, I have a question for you. In slide number 6, in one of your presentation,
Yes.
there's somewhere I saw you expressing a temperature in terms of electron volts.
Yes.
Yes.
Temperature.
Yes. Can you look at that slide number 6?
Just a minute. Slide number 6.
Yes, number 6.
Let me just go there.
Okay, while he's going there, Bill Oyomo, I have a question while he's opening his PowerPoint.
Yeah.
For Bill Oyomo.
Yeah.
Oh, Kennedy is already there?
Yes.
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 Yes. Can you the last bullet? The temperature of 090.
Yes, I change it into.
Good for that clarifications. We go to slide number 10. No number. Kennedy? Yeah?
Yes.
Slide number 8. My question is, when you are given the Brillouin zone, how do you select these points of the highest symmetry? Gamma, X, Y, sigma, gamma, Z? How can you explain to the audience, how do you select points of highest symmetry?
Okay, this one, for us to identify the points of symmetry, first we have to look at where the system has relaxed. And we also look at the band structure. After relaxing that particular system, we look at where the system has relaxed and has minimum energy. That is where we can be able to find the symmetrical points.
When you consider the atoms and the bases for the whole crystal structure,
yes,
and then now you have already come up with the Brillouin zone.
Yes.
Now, when we are looking at that drawing of the Brillouin zone, do you rely only on the relaxation or identifying these points of symmetry?
Okay, the thing is, after relaxing the system, we can be able now to find the symmetrical points. You can be able to guide us now to get the symmetrical points from the material project.
Okay. Yes. And now, since you had already done your work using a generalized gradient approximation, what could have happened if you had used local spin density approximation?
Okay, when you are using the local, the LDA, in most cases it has the underbinding of the band structure. Although in this case I used the GGA, which at times has overbinding, but in this case I realize at times when you are doing the calculation, we have some other noise in the system, which may bring some slight deviation in the results as compared to the experimental values.
Okay, thank you. Further question from the floor? Further questions from the floor? Anybody with a question? Maxwell Mageto, do you have a question?
You have the Maxwell Mageto now. What is it, man? Not one.
We have somebody talking because Mageto has muted. Do you have any question? Any question? There being no further questions, let me hand over the floor to the main chair, Professor Julius Mabora. Mabora, back to you.
Hello. Thank you very much. I'm working from Maxwell's Mageto's computer. Mine has hanged. Are you hearing me?
Yes.
Hello?
Yes.
Yes, we can hear you, but there are two mics which are on. Bill, can you switch off your mic? Kennedy, can you switch off your mic?
Hello? Hello? Are you hearing me?
Jogo Muyuki, can you switch off your mic?
Hello? Hello?
Hello? Hello?
Yes, now we can hear you.
Okay,
the mics
fine.
are off now.
I'm talking from Dr. Mageto's computer. Mine has hanged. I really want to thank all the chairs of session, rapporteurs, and the participants for today's conference. We have kept time, and thanks to the rapporteurs, the presenters, I think all of them presented except one who did not present. So tomorrow we meet again. The program begins at exactly 8:30 sharp. So we should start joining at 8. So that by 8:30 sharp we'll begin presentations. For the rapporteurs, send your reports. Please send your reports to Dr. Grace Kinunda. I'll send you the email. You can copy it to the Msseesa email. So I'll email you these details so that we can compile our rapporteur's report. Otherwise, thank you very much. I don't know whether the Professor Diale is there, but is she there? Is she able to speak? Dr. Diale from the University of Pretoria. Okay, if she's there. Hello? Yeah, she can't speak. It looks like she can't speak. We'll hear from her when she's giving her presentation. So thank you very much. So the session for today is closed. Have a good evening and thank you. Bye.